A gas turbine operates by drawing in fresh air, then compressing it to a higher pressure through its axial flow compressor. Next, fuel is added to the compressed air and burned, which raises the energy level. This high-pressure, high-temperature air is then sent to an expansion turbine, where the gas energy is converted to the mechanical energy of a rotating shaft. The conversion of work in the turbine actually takes place in two steps. In the nozzle section of the turbine, the hot gases are expanded and a portion of the thermal energy is converted into kinetic energy. In the subsequent bucket section of the turbine, a portion of the kinetic energy is transferred to the rotating buckets and converted to work. Typically, more than 50% of the work developed by the turbine section is used to power the axial flow compressor. Since the gas turbine is an ambient air breathing machine, its performance will be changed by anything affecting the mass flow of the air intake to the compressor. The most obvious are changes in the reference conditions of 59 degrees Fahrenheit and 14.7 psia. Depending on the unit's cycle parameters and component efficiencies, ambient temperature will affect the air mass flow, which in turn will change output, heat consumption, heat rate, and exhaust flow. When burning lower heating value fuels, turbine mass flow is increased because more fuel and air are required. This drives up the compressor pressure ratio, eventually encroaching on the compressor surge limit. This means that such a large volume of fuel is required to fire the machine that it begins to push back on the compressor discharge pressure, causing a reverse flow to occur in the compressor. The compressor rotor is assembled by vertically stacking the wheels. First, the compressor forward stub shaft and first wheel are put into the stacking pit with tie bolts in place. Then each wheel is slid vertically over the tie bolts. In the case of the MS7000EA, there are a total of 17 wheels on the compressor rotor. Once the last wheel and aft stub shaft are stacked, the tie bolts are then torqued. Once the compressor rotor is assembled, it is slow-speed balanced to make sure vibration levels meet design standards. GE is a leader in rotating equipment and vibration analysis. Also, field and service shop balancing can be done after the unit is in service. The first step of the assembly of installing the first stage buckets to the turbine wheel is to insert the radial locking pin into the locking bucket dovetail. The first bucket is installed in the counterclockwise adjoining dovetail slot and is held in place with a D key. The remainder of the buckets are installed in this fashion, working around the wheel counterclockwise. The last bucket is installed into its dovetail, and the axial locking pin is driven into the wheel. This pushes the radial locking pin up to hold the last bucket in place. All the buckets are now locked onto the turbine wheel. Before the second and third stage buckets are installed, twist locks are put in place. Then the buckets are installed as a 360-degree ring. The ring is worked into the wheel gradually due to the interlocking Z-lock. Once they are installed, the twist locks are rotated to lock them in place. GE is a leader in rotating equipment and vibration analysis. Once the casings are on, the combustion system is installed. Next, the shell cooling air piping is installed. Air comes from off-base blowers to facilitate shell cooling in the turbine and exhaust casings. Then the inlet plenum is installed. After this, the exhaust plenum is put in place. The flex seals keep the exhaust gases from escaping into the turbine compartment or out to atmosphere while allowing for thermal expansion. Finally, the compressor bleed valves are installed. These are operational during startup and shutdown to protect the unit from surge. The number 1 bearing is installed in the inlet casing. and the number 2 and number 3 bearings and housings are placed into their respective casings. The lower half is put in first. Then the upper half of the bearings and housings are installed. Then the bearings are aligned with the casings installed. The upper halves of the bearing housings and casings are then removed, and the air seals and oil deflectors are installed. The final step is the installation of the rotor and the upper halves of the bearing housings and casings. To assemble the first stage nozzle, the nozzle segments are installed into the support ring. Seals are installed to minimize gas leakage. Alignment pins are then installed to radially align the segments in the ring. To assemble the second stage nozzle, first a core plug is installed in the investment cast piece to allow for even cooling down the center of the bore of the nozzle segment. The diaphragm section is then attached and a pin is installed for nozzle to diaphragm alignment. Wheel space cooling tubes and plugs are installed in the diaphragm. The third stage nozzle is similar to the second stage nozzle, but it is not forced air cooled, so there is no core plug and there are no cooling tubes. The assembly of the combustion system begins with the transition piece bolted to the first stage nozzle on its aft end and supported by the bullhorn bracket on its forward end. Next, the combustion casing is bolted onto the combustion wrapper. Then the flow sleeve slides into the casing. The crossfire tubes are then installed, but pushed out of the way so that the liner may be installed. Once it is, the crossfire tubes are put into the crossfire tube collars in the liner. Retaining clips keep the crossfire tubes in place. Next, the combustion can cover is bolted onto the combustion casing. And then the fuel nozzle is installed onto the combustion can cover. Spark plugs and flame detectors are also installed on certain combustion cans depending on the vintage of the unit. As you know, the upper halves of the casings are removed to allow for internal component installation. All vertical and horizontal bolts are removed, and the casings are lifted off one at a time in the following sequence. First the turbine shell, then the compressor casing, then the inlet casing, then the exhaust casing, and finally the compressor discharge casing. To give you a mechanical analogy, check valves behave the same way as diodes in electrical systems. In this analogy, a fixed pressure to the main manifold is provided by the supply tank. The pressure at the main manifold can be regulated by the check valves A, B, or C. For example, the pressure at point 1 is considered constant at 20 psi. If the pressure at points 2, 3, and 4 are higher than 20 psi, then there will be no control of the pressure at the main manifold. If the pressure at point 2 decreases to 18 psi, and the pressure at points 3 and 4 remain the same, then the pressure at the manifold will be brought down to 18 psi, and System A is controlling. As the operating conditions change, the pressure requirements at points 3 and 4 change. As the pressure, say, at point 3 drops below 18 psi, for example 17 psi, the manifold pressure will be brought down to 17 psi, causing check valves A and C to close, and check valve B to open. Therefore, system B is now controlling. The startup control loop controls the rate of fuel addition for several reasons: to establish flame in the combustors, to control the acceleration rate, and to control the rate of temperature change. Acceleration of the turbine rotor must be controlled so as not to exceed the allowable forces on the rotor. Exceeding the limit can cause heavy damage to the rotor. During startup, the airflow rates are low. If there is too much fuel added to the combustors while there isn't enough air, temperatures could get dangerously high, potentially damaging internal hardware. And high fluctuations in temperature can reduce the life of the internal hardware. Different materials heat at different rates, so the rate of temperature change must be limited at approximately 5 degrees per second. The electronic overspeed protection function is performed as shown here. The turbine speed signal derived from the magnetic pickup sensors is compared to an overspeed set point. When the turbine speed signal exceeds the set point, the overspeed trip signal is transmitted to the master protective circuit to shut down the turbine. An electrical overspeed trip message will be displayed. The fuel gas pressure transducer has a DC voltage output directly proportional to pressure input in PSIG. This transducer provides the control system with a feedback signal for the operational fuel gas pressure, or P2 pressure, between the stop speed ratio and gas control valves. The fuel gas vent solenoid valve vents the volume between the stop speed ratio valve and the gas control valve when the solenoid is de-energized. This valve is closed during operation. When it is open, it ensures that during the shutdown period, fuel gas pressure will not build up between the stop speed ratio valve and that no fuel gas will leak past the closed gas control valve. Welcome to the Help menu. Selecting any button will show information about its function. The Help menu button will return you to this screen. When you are finished, the Exit Help button will return you to the course. This yellow band is the button highlight. It is used to recommend a logical path through the course. The suggested path is highly recommended for first-time users. Between which 2 points in the Brayton cycle is the pressure constant and the volume of the hot gases increasing? Sorry, your choice is incorrect.